Hello and what's up guys? In this video, I will be repairing and refurbishing this old inverter welding machine. You can see these marks on the screw hole where somebody previously used a grinder to remove the screws. It happened because the screws became rusted, and that means this unit has not been opened for a really long time. These are the better quality inverter welding machines. You can see the inside is very dusty from long time of use. The fact that it has been used for a long time tells you that it is built to last. Most of the cheaper models that I have repaired have boards that are very clean and looks brand new. That shows that they break down easily in just a short time. I removed the main board and you can see that this model uses these big aluminum heat sinks compared to cheaper models. You can also see that the board has provision to use additional IGBTs as well as additional fast recovery diodes. That should make this inverter welder even more long-lasting. Before I proceed, I will first clean this board with detergent soap and water because this is so dirty. Here is the board after cleaning and look at the difference that it makes. This now looks like a completely different board. So the problem with this machine is that when the user turns on the switch, the circuit breaker in the house will trip. So my first suspect are the IGBTs and the fast recovery diodes. I am using the diode check function of the multimeter to make a quick check of this IGBT even while it is still in the board. As you can see, all of the pins are shorted to each other. The other IGBT has the same condition. All the pins are shorted. Later in the video, I will show you the same test with a good IGBT. I then test the fast recovery diodes, and as you can see, when the black probe is on the cathode, which is by the way is electrically connected to the heatsink, and the red probe on the anode, we are getting the diode voltage. And when I reverse the polarity of the probes, we are getting OL or open lead on the multimeter. That is how it should be and means that the diode is good. I already removed the two shorted IGBTs, but before I replace with a new one, I will first walk you through the basic checks I do with these inverter welding machine boards. First, I check if there is 310 volts DC, and we can test that on this 3-pin header. This board is producing 310 volts DC, so I proceed with the next test, which is checking the output of the auxiliary power supply. The auxiliary power supply produces the low voltage DC supply to the PWM controller, the fan, and the relay. It has this switching power supply section and this step-down transformer. Near the transformer, there are rectifier diodes and filter electrolytic capacitors. We can check the DC output of the auxiliary power supply at the pins of the rectifier diodes. I probe the cathode pin of the diode and is getting 15 volts DC. I probe the cathode pin of the other diode and is getting 25 volts. Those are the normal output voltages of the auxiliary power supply, and so this section is okay. This particular unit uses this PWM controller module board with the SG3525 IC. I will be checking if this IC is working normally by probing some of the important pins with the voltmeter. Pin 16 is VREF and should be getting about 5.1 volts. Pin 15 is VCC supply voltage, so it should have about 15 volts from the auxiliary power supply. Pin 14 is the output B of the IC, and with the voltmeter, we should be getting somewhere about 6 volts. Pin 13 is supply voltage to the internal output transistor of the IC, and should be close to VCC value. Pin 12 is ground, so should be 0 volt. Pin 11 is output A of the IC and should be about 6 volts, just like pin 14. Pin 10 is connected to ground, so 0 volts. And pin 9 should be about 4 volts. Those are the normal voltage values to the important pins of the SG3525 IC. The output A and B of the SG3525 IC drives these two MOSFET ICs to produce the AC waveform going to the primary coil of this gate drive transformer. I connect an oscilloscope to the primary winding of the gate drive transformer, and we can see the AC waveform produced from the PWM controller. And that is how I check to see if the PWM controller is working fine. After making those basic checks, I then installed the new IGBT. This is what a good IGBT that is already soldered on the board shows on the diode check function of the multimeter. With the black probe on the collector and the red probe on the emitter, we should be getting diode voltage. If we reverse the probe, red on the collector and black on the emitter, should be OL or open lead. Then, gate to collector should be high resistance, no beep. If you test the gate to emitter, the meter beeps because those are connected to the secondary coil of the gate drive transformer, and it has low resistance, so that is normal. After just replacing the two IGBT, the board now has the output voltage of about 50 volts. Usually when the IGBT got shorted, it also damages some resistors in the gate drive circuit, but that is not the case with this board. No other components were replaced aside from the two shorted IGBTs. I put back the board to the case and test the welder. It is now working good as new. If you find this video helpful, please click the like button and consider subscribing to my channel. Thank you for watching, and I hope to see you next time.